Hi everyone. This is the topic on sufficiency. This is a continuation on the topic of completeness and uniqueness. Let the parameter theta in the probability density function given as fx theta have a sufficient statistic y1, where x1, x2, xn is a random sample. Let the probability density function of y1 denote as g1 y1 theta. Note that if there is any unbiased estimator y2, then there is at least one function of y1 that is an unbiased estimator of theta, and our search for the best estimator of theta may be restricted to function of y1, where in this case y1 is a sufficient statistic. Suppose it has been verified that a certain function phi y1 is not a function of theta, such that expected value of phi y1 is equals to theta. Let's say if we have another function which is upside y1 be another function of the sufficient statistic of y1 alone, so that we also have expected value of upside y1 is equals to theta for all values of theta. Hence, we can simplify that expected value of phi y1 minus upside y1 is equals to 0 for all theta belong to omega. And if the family of g1 y1, which is the family of sufficient statistic, is a complete family, then the function phi y1 minus upside y1 can be written as equals to 0, except on a set of points that has probability 0. That is, for every other unbiased estimator upside y1 of theta, we will have phi y1 is equals to upside y1, except possibly at certain points. Thus, we call that phi y1 is the unique function of y1 and it is unbiased estimator of theta. And according to the Rao-Blackwell theorem, phi y1 has a smaller variance than every other unbiased estimator of theta. So if the condition happen where phi y1 has a smaller variance than every other unbiased estimator of theta, then the statistic phi y1 is the unbiased minimum variance estimator of theta. So this relates to another theorem where we call as theorem of Lemon and Schaeffer. Let's say if we have a random sample from a distribution that has probability density function or probability mass function fx theta. And if we have y1, a sufficient statistic for theta, and then let's say if we have the family of fy1 is a complete family. And if there is a function of y1 that is an unbiased estimator of theta, then this function of y1 is the unique minimum variance unbiased estimator of theta. So this describes the theorem of Lemon and Schaeffer, where we have y1 is a sufficient statistic for theta, and if the family is a complete family, if there is a function of y1 that is unbiased estimator of theta, then this function of y1 will have, or we will consider as the unique minimum variance unbiased estimator of theta. Suppose that we have example given as theta to the power x, 1 minus theta to the power 1 minus x, where x takes value from 0 and 1. So this is the Bernoulli distribution. We want to show that y equals to summation xi is a complete sufficient statistic for theta. So how we want to show that y is a complete family? First, if we construct the joint PDF, so we will have theta to the power summation xi, 1 minus theta and minus summation xi. So we rewrite, we have theta to summation xi, 1 minus theta to the power n, 1 minus theta to the power minus summation xi. So we will have theta over 1 minus theta to the power summation Si, 1 minus theta to the power n. So by factorization theorem, y equal to summation Si is a sufficient statistic for theta. So how we want to verify whether the family of PDF is a complete family? So since y is a sum of independent Bernoulli random variable, so we will have a binomial distribution, where we can write y is distributed as binomial NP, where p take values from 0 up to 1, and y is equals to 0 up to n. Let's say if we have gy, another function, we want to show that expected value of gy is equals to 0. So we will have summation y equals to 0 up to n, gy times the probability mass function for binomial, where we have n choose y, p to the power y, 1 minus p to the power n minus y. So we rewrite the equation. So we have 1 minus p to the power n, summation gy, n choose y, p over 1 minus p to the power y, where we simplify the equation of p to the power y, 1 minus p to the power minus y. Let's say we denote r is equals to p over 1 minus p with the condition r is greater than 0. So we can rewrite the equation. We will have gy, n choose y, r to the power y. So let's say if we have hy be a function or denote as gy n choose y, so we can simplify this one by writing hy r to the power y. So for the expression to be 0, okay, the coefficient hy must be 0, since our r must be greater than 0. So it means that hy is equals to 0 for all y values. Hence, the probability of hy equals to 0 is equals to 1. So by the definition of complete family, y is a complete sufficient statistic for theta. Okay, so we have one example how we want to show that y is a sufficient statistic, and then the second step we show how y can be a complete sufficient statistic by showing that the family of y is a complete family. So second part, we want to determine the uniqueness. So we have y equals to summation Si. So now we want to find expected value of y. So it can be written as expected value of x1, x2, Sn. So since expected value of x1 is equal to theta, expected value of x2 is also theta. So altogether we have n theta. So by rewrite the equation, expected value of y over n is equals to theta. So this shows that theta head is equals to y over n is a unique minimum variance unbiased estimator of theta. So hence, this complete our question where we want to show that it is a complete sufficient statistic and it also have a unique minimum variance unbiased estimator of theta. So that's it. So see you again in our next example. Bye.